Hello students, welcome back to the lecture series of rotational dynamics. The first topic that we are going to see today is moment of inertia. So let's start with the definition. As I've written on the screen, the moment of inertia of a rigid body about an axis of rotation is nothing but the sum of product of mass of each particle and the square of its perpendicular distance from axis of rotation. So while calculating the moment of inertia for a rigid body, what we do is we take all the masses on the rigid body, then we multiply all the masses of the rigid body by the perpendicular distance of each mass from the axis of rotation. Just before multiplication, we square the distances. So what we get is a quantity which is nothing but product of mass and the square of the distance of the mass from the axis of rotation. And when we do this finally for all the masses, what we just do is addition of all the values that we have got. So for example, I've taken mass 1 on rigid body, then mass 2 and mass n. So this rigid body on the left hand side of the screen has multiple masses from m1, m2, so on up to mn. And R1, R2 and Rn, R1, R2 and so on up to Rn are nothing but the respective distances of the masses from the axis of rotation. So from the above definition, what we first need to do is to calculate the product. Product of what? Mass and the square of the distance of that mass from the axis of rotation. So we will calculate that. So for first mass, it is m1 r1 square. For second mass, it is m2 r2 square. And so on up to, for the nth mass, it is mn rn square. And what we do finally is nothing but add these products. So moment of inertia is nothing but m1 r1 square plus m2 r2 square, so on up to mn rn square. Now, this can be easily represented by a summation symbol. So I can write down summation I is equal to 1 to n mi ri square, where I goes from 1 to n. Now, we have to find out the SI unit. We know that the moment of inertia is nothing but the product of mass and the square of the distance. So the unit of mass is kg and the square of the distance will have unit meter square. So the SI unit of moment of inertia is kg meter square. Now from this unit we can easily write down the dimensions. Kg, therefore we have mass to power 1. Meter square, therefore we have length to power 2. And there is no unit of time, that is second, therefore t to power 0. Now, an important point to notice is that as we increase these values of R1, R2, R3, so on up to Rn, the moment of inertia increases. So as we increase R1, R2, R3, Rn, the moment of inertia also increases. Now, the point that I'm trying to make over here is that as we move the masses away from the axis of rotation, the moment of inertia increases. So we can note an important point over here, which is if mass is concentrated, closer to axis of rotation, moment of inertia has a smaller value. Moment of inertia has a smaller value. But if the mass is concentrated away from axis, the moment of inertia has a larger value. So closer the mass is concentrated to the axis of rotation, smaller is the value of moment of inertia. Farther the mass is concentrated from the axis of rotation, larger is the value of moment of inertia. Okay. After studying moment of inertia, we need to define radius of gyration. So let's first read the definition. So radius of gyration of a body about a given axis is defined as distance between the axis of rotation and a point at which whole mass of the body can be assumed to be concentrated such that it has same moment of inertia as that of the body about the same axis. Now this is the definition, but let's not understand it in a rudimentary manner by learning the definition. Let's see what is actually given in this definition. So for that, I have considered the body on the left hand side. So we have a weird shaped body on the left hand side of the screen whose mass is m. Then we have defined the axis of rotation over here, and around that axis of rotation, the moment of inertia of the given body is I. So we have a body whose mass is capital M. We have shown the axis of rotation, and about this given axis of rotation, the moment of inertia is I. If we change the axis of rotation, the moment of inertia is also going to change. Okay. Now, what I do is I take this whole mass over here and convert it into a point particle. So this is the point particle on the right hand side of the page. This is the same axis. The axis has not changed. So the left hand side axis and the right hand side axis are same. So what we have changed is just the body. Initially we had a body which was extended, spread, and now we have converted that body into a point mass, keeping the mass same. We have converted it into a point particle by keeping the mass same. We have kept the point particle at a distance k from the axis of rotation. Now, for point particles, the moment of inertia is mr square. But the mass we have is m, and the distance that we have for this point particle from the axis of rotation is nothing but k. And what we are getting is I dash. I dash is nothing but moment of inertia of this point particle about the axis of rotation, and we are getting it mk square. Now, if the moment of inertia initial and this I dash are same, then we can say that this distance k is nothing but the radius of gyration. So to find out the radius of gyration, what we do is we take the extended body, we convert it into a point mass, and we place it at a distance, let's say k. Then we find the moment of inertia of that point mass about the same axis, and we get mk square. We get mk square. This moment of inertia of the point particle mk square is same as that of the moment of inertia of the extended body. We have done this by keeping the axis of rotation same. And when all these conditions are satisfied, we call this distance k as the radius of gyration. So, to find out the radius of gyration, what must be done? So, to find out the radius of gyration, first we require a body, and an axis of rotation must be defined for the body. So, when we have a body and we have an axis of rotation, we can calculate moment of inertia of the body about that axis of rotation. And once we get the moment of inertia of the body about that axis of rotation, we just equate it to mk square. And what we do is find out the value of k. Once we find out the value of k, we get the value of radius of gyration. But an important point to note over here is that, as I said, to find out the moment of inertia, we require a body and an axis of rotation. So what happens when the axis of rotation changes? So we know it depends on axis of rotation. Therefore, as we change the axis of rotation, the radius of gyration also changes because I itself changes. I itself changes. So when axis changes, I changes. Therefore, radius of gyration also changes. Radius of gyration also changes. Now, I have considered two examples over here. The bodies are nothing but spheres, but I have changed the axis of rotation. And what we have to do is we have to calculate the radius of gyration of the sphere about the mentioned axis. So since the axis of rotation is changing in both the cases, the radius of gyration should also change. And let us see how it changes and practice how to calculate radius of gyration. So for the first case on the left hand side, I'll do the calculations. Okay. So I have been given that I is equal to 2 by 5 mr square. Now, as I said, to find out the radius of gyration, I have to equate it to mk square. Now, m is nothing but the mass of the same body. So we can cancel m, and finally what we get is k square is equal to 2 by 5 r square, and k is equal to under root 2 by 5 r. So when a sphere is given and it is rotating about an axis of rotation which is passing through the center of the sphere, then in such a case the radius of gyration is under root 2 by 5 r. Now let's change the radius. Let's change the axis. So we have changed the axis, and now the axis is not passing through the center, but it is along the tangent to the sphere. And along that tangent, the moment of inertia for the sphere is given as 7 by 5 mr square. Now, how did I get 2 by 5 mr square about an axis passing through the center, and how is the moment of inertia 7 by 5 mr square about the tangent to the sphere? All these topics are for another video. By the way, I've uploaded a short. You can go and check out the short where I've mentioned the moment of inertia for different bodies. But I'm not going to explain how is it 2 by 5 mr square for axis passing through center and 7 by 5 mr square for about the tangent. That is the topic for another video. For now, just assume that these are the moment of inertias. We just have to see the calculation of radius of gyration. So to calculate the radius of gyration, what did I say? We just equate the moment of inertia, which is 7 by 5 mr square in this case, to mk square. M is the same mass, so it gets cancelled. And finally, what we have is k square is equal to 7 by 5 mr square. So k in this case, what we have is under root 7 by 5. I'll write an extra m over here. So 7 by 5 r square. So k is equal to under root 7 by 5 r. So as we can see, for the same body, if we are changing the axis of rotation, the radius of gyration is also going to change. And this happens because once we change the axis, the moment of inertia itself changes, and therefore the radius of gyration is bound to change. So I was thinking to make a different video for this topic, but it's a very small topic and I thought of finishing it now. So let's start with this topic and end the lecture with this topic. So the topic is rotational kinetic energy. So when the body moves in a straight line, linear motion, we define a linear kinetic energy, and its formula we know that it is nothing but half mv square, half into mass into velocities square. In the similar manner, when a body rotates about an axis of rotation, we can define rotational kinetic energy. And what we are going to do over here is derive the formula for rotational kinetic energy. So let's start with the derivation. So the first point that we think of over here is when the rigid body rotates about an axis of rotation, the particles of the rigid body, they perform circular motion. Now we have discussed this in detail in the first lecture. If you haven't watched first lecture, please go and watch the first lecture. So I'll repeat the point that when a rigid body rotates about an axis of rotation, all the particles on the rigid body, they perform circular motion. Now, since all the particles are performing circular motion, obviously they'll be having some tangential velocities, and that tangential velocity can be found out by using the formula V is equal to R omega. So I've shown some particles on the left hand side of the rigid body, which is particle having mass m1, particle having mass m2, so on up to particle having mass mn. So there are n particles for which I can write that in the tangential velocities like V1 is equal to R1 omega, V2 is equal to R2 omega, V3 is equal to R3 omega, and so on up to Vn, which we can write down as Rn into omega. Now a point to notice over here is the tangential velocities are different for different particles because the distance of all the particles from the axis of rotation is different. But the angular velocity is same for all the particles. So the angular velocity of the rigid body is nothing but the angular velocity of all the particles, which is nothing but omega. Now, Since these particles that are performing circular motion have some tangential velocities, let's call them velocities, v's, so we can calculate their kinetic energies. So for the first particle, the kinetic energy is half m1 v1 square. For second particle, it is half m2 v2 square. And so on up to, for the nth particle, we can write it as half mn into vn ka square. So these are the kinetic energies of all the particles that are on the rigid body and are performing what? Circular motion. And they are performing circular motion because the rigid body is rotating about the axis. Let's move further. So what we say is that the kinetic energy of the rotation is nothing but the summation of the kinetic energy translation of all the particles. So we have kinetic energy of all the particles, which is half mv square. If we add all those kinetic energy of the particles, the energy that we get is nothing but the rotational kinetic energy of the rigid body. So we can find out the rotational kinetic energy. So kinetic energy rotational is nothing but kinetic energy translation of the first particle, kinetic energy of second particle, plus kinetic energy of third particle, so on up to kinetic energy of nth particle. Now, if we plug in the values of the kinetic energies, what we get is half m1 v1 square plus half m2 v2 square plus half m3 v3 square and so on up to half mn vn ka square. Now, we know v is equal to r omega. So v1 is equal to r1 omega, v2 is equal to r2 omega, and so on up to vn, which is rn omega. Let's plug in the values of v's. So half m1, in place of v1, I can write down r1 square omega square. Half m2, in place of v2 square, I can write r2 square omega square. In place of v3, I can write down r3 square omega square, and so on up to half mn. In place of vn square, I can write down rn square omega square. Now from all the terms, we can common out half and we can common out omega square. So half I am taking on the left hand side. So inside the bracket, I have m1 r1 square plus m2 r2 square plus m3 r3 square and so on up to mn rn square times omega. Now, if you look at the term which is inside the bracket, it must click you that it is nothing but moment of inertia of the body. So we can write down in that bracketed term, in place of that bracketed term, we can write down I. And so we get the formula half I omega square. So the rotational kinetic energy is nothing but half I omega square, where I is nothing but moment of inertia, omega is nothing but angular velocity. So we have the formula for rotational kinetic energy. Let's compare it with translational kinetic energy. Translational kinetic energy is half mv square. From these two formulas, we get another analogous quantity which compares linear motion and rotational motion. So we know that when we go from linear motion to rotational motion, we replace s by theta, then we replace v by omega, then we replace the acceleration by alpha, and in a similar manner, by comparing the formulas of translational kinetic energy and rotational kinetic energy, we see that we can replace mass with nothing but moment of inertia. So the quantity analogous to mass in rotational motion is nothing but moment of inertia. So that's all for today. Thank you, students, for attending the lecture. Bye.